In this video, we'll learn how to conduct hypothesis testing for proportions, first by using the formulas, then by using a TI-84 graphing calculator. Before we begin working on an example problem, there are some definitions that you need to know. First, HO, the null hypothesis or statement of no effect. HO is the model, and it contains the statement of equality. HA, our alternate hypothesis, contains the claim most, but not all of the time. P-value, this is our probability value. If the p-value is small, evidence for rejecting HO and failing to reject HA is stronger. When is a p-value statistically significant? To determine this, we use what's called an alpha level. Symbolized by the Greek letter alpha, this is the threshold we can arbitrarily set to define a rare event and determine whether a result is statistically significant. Common alpha levels are 10%, 5%, or 1%. They're generally represented in their decimal form, and 5% is the most common. An alpha level of 5% is a typical cutoff. It corresponds to a 95% confidence level. An alpha level of 1% is used in more stringent tests. It corresponds to a 99% confidence level. Note that hypothesis tests for proportions use z-scores. When conducting hypothesis tests for proportions, we need to also take into consideration certain assumptions and conditions. First, we must consider independence. In other words, our samples need to be independent of one another. Randomness. Our samples should be selected they should be randomly selected from a population. 10% condition. Our sample must represent less than 10% of the population. Our success-failure condition. N times P must be greater than 10, and N times Q must be greater than 10. In other words, our sample size times the probability of success must be greater than 10, and our sample size times the probability of failure must also be greater than 10. Some textbooks may suggest that the success-failure condition dictates that N times P be greater than or equal to 10, and N times Q greater than or equal to 10. That's okay too. Now let's take a look at an example. Television violence. In 1996, the University of California at Santa Barbara reported that 57% of television programs contain violence. In 2012, the American Academy of Family Physicians reported 66% of television programs contain violence. Using a sample size of 500 viewing hours, test the claim that the percent of television violence has significantly increased from 1996 to 2012. Test an appropriate hypothesis and state your conclusion. Be sure the appropriate assumptions and conditions are satisfied before you proceed. Let's begin by establishing our null and alternate hypothesis. Remember, the null hypothesis, or statement of no effect, contains the statement of equality. Our null hypothesis is that our proportion is equal to 57%, which we'll write as a decimal, 0.57. Our alternate hypothesis is that P is less than 0.57. that p is greater than 0.57. So our null hypothesis is that p is equal to 0.57. Our alternate hypothesis is that p is greater than 0.57. The reason why we choose the greater than symbol is that we're testing the claim that the percent of television violence has significantly increased from 1996 to 2012. First, we'll look at the independence condition. We can reasonably assume in this case that the viewing hours are independent. In other words, the number of hours viewed by one person differ from the number of hours viewed by another. We can even assume that one viewing hour is independent of the next, even if watched by the same person. When we do this, we're taking more of a theoretical approach. As we all know that when you watch television, you probably have a tendency to like particular types of shows. But in this case, we're going to assume that each and every viewing hour is independent of the next. When we check our randomization condition, here's where we'll take into account possible repetition of content. The channels were not chosen randomly. Some repetition of viewing content may have occurred during the 500 hours. In addition, the channels selected for the study may have been geared towards specific genres. Proceed with caution. Our 10% condition is satisfied, as 500 viewing hours is certainly less than all possible viewing hours. Our success-failure condition is also satisfied. N times P equals our sample size, 500, times our probability of success, 0.57. That gives us a result of 285, which is greater than 10. Our probability of failure, N times Q, gives us 500 times 0.43. Q is the complement to P. So because the probability of success is 0.57, the probability of failure is 1 minus the probability of success. That's how we get 0.43. That product, 500 times 0.43, is 215, which is also obviously more than 10. So this condition is satisfied. Because our assumptions and conditions have, for the most part, been satisfied, other than this one, which we just want to be cognizant of, the normal model would be appropriate. So we'll proceed with our calculations. We already know that P is represented by 0.57. This percentage is also known as our population proportion. We're going to use this value along with our P hat value, 0.66. And we haven't talked about P hat yet, but what P hat is our sample proportion. In other words, that 66% is the value that the American Academy of Family Physicians generated through their report. It's our sample that we're comparing to our original given population proportion. We need to also find the standard deviation for P hat in order to be able to proceed with our calculations. The standard deviation for P hat, in other words, the standard deviation for our sample proportion, is found by taking the square root of P, our population proportion, times Q, the complement to our population proportion, in other words, our probabilities of success and failure, divided by our sample size, N. So the standard deviation for P hat will be 0.57 times 0.43, all divided by our sample size of 500. Working this out gives us 0.022. This is our standard deviation for p hat. Once we have p hat, and our standard deviation for p hat, we have everything we need to generate our z-score. We'll use this z-score to help us determine whether or not p hat of 0.66 or 66% is statistically significant. In other words, we're going to use our z-score to help us decide whether the percent of television violence has significantly increased from 1996 to 2012. For our z-score formula, we'll use p hat minus p divided by the standard deviation for p hat. In other words, our sample proportion minus our population proportion divided by the standard deviation of our sample proportion. Plugging in our values, we have 0.66 minus 0.57 divided by 0.022. Our result is 4.09. In other words, just a little bit more than 4 standard deviations above our population proportion. Let's take a look at this within the context of the normal model. Looking at the normal model, we can see that our sample proportion, p, centered at the mean, and our sample proportion, p hat, 0.66, which is 4.09 standard deviations above the mean, represent what we might consider to be a statistically significant result. In other words, looking at our z-score of 4.09, it's already looking as though the percent of television violence has significantly increased from 1996 to 2012. But before we can say that for sure, we need to calculate the probability. In other words, in the likelihood that 57% of television programs contain violence, for a sample like this one, how likely is it that we would see another sample where 66% of television shows contain violence? We want to know what is the likelihood of 66% occurring if the 57% is true. At this point, you can use a z-score table to look up the probability. In your table, you can look for a z-score of 4.09 and find the associated probability that corresponds to it, or we can use our calculator to calculate the value. Using a graphing calculator, you'll hit the second key, then distribution, which is above variables. Then you'll choose option 2, normal CDF. From here, you'll be asked to establish a lower bound and an upper bound. Now, because we're looking to see whether the percent of television violence has significantly increased, we're going to set our lower bound at 4.09, our z-score, and our upper bound just needs to be some value that's off the curve. You can use 5, 10, 20. I usually use 100 as my default value for upper bounds. So if my lower bound is my z-score, then I use an upper bound of 100. If I were working the other way around, I would let my lower bound be negative 100 and my upper bound be whatever z-score I had. But in this case, we'll use 4.09, 100. This gives us the result 2.16 times 10 to the negative 5. This is an extremely small probability. In other words, we're saying that in a sample like ours, the likelihood of achieving a value of 66%, given that 57% is the accepted proportion, would happen 0.0000216 of the time. If we convert that to a percentage, it would be 0.00216%. As you can see, to convert from decimal to percent, I simply move that decimal place 2 to the right. So, what does this tell us? Is our result statistically significant? Suppose we wish to set an alpha level of 5%. In other words, any probability value smaller than 5% will be statistically significant. Well, in this case, we can see that 0.00216% is much smaller than 5%. So our sample evidence supports the claim that the proportion of violence on television in 2012 is significantly higher than the proportion of television violence in 1996. For this example, we could even set our alpha at 1%, and we would still find that the sample evidence supported the claim. So once again, in conclusion, we can state that the sample evidence supports the claim that the proportion of violence on television in 2012 is significantly higher than the proportion of television violence in 1996. Now let's take a look at how we would solve this using our graphing calculators. We've established that our null hypothesis is 0.57 and our alternate hypothesis is greater than 0.57. So Ho is equal to 0.57 and Ha is greater than 0.57. It's our null hypothesis and our alternate hypothesis. In this case, our claim is in the alternate. Once you open up your one proportion z-test menu, you'll type in 0.57 and your p sub 0. This is for your null hypothesis. Then you'll type in an x value. We type in 330. Where did that come from? That number came from taking our sample size of 500 and multiplying it by p hat, 0.66. In the next field, we put our sample size, n, of 500. Then we need to determine whether we're conducting an inequality test, a less than test, or a greater than test. Well, since we know that we're looking to see whether the proportion of violence on television is significantly higher, then we're selecting the greater than. Below this, you have the option to select either calculate, which is obscured because we have it highlighted, or draw. Calculate is what you want. So you highlight this and then you press enter. When we press enter, we get the following results. Z is equal to 4.06, and our p-value is 2.4 times 10 to the negative 5. In other words, 0.00024 or 0.0024%. Now you may notice slight discrepancies between working problems out by hand and using your calculator, and that has to do with decimal rounding issues. For example, when we worked out our problem, our z-score was 4.09. In this case, z is equal to 4.06. These are minor differences that are to be expected when using different methods to solve the problem. But again, we can draw the same conclusion. The sample evidence supports the claim that the proportion of violence on television in 2012 is significantly higher than the proportion of television violence in 1996. This will be true whether you use a 5% or 1% significance level. So now we've looked at the basics for conducting a hypothesis test for proportions, as well as some of the basic terminology and definitions.